Welcome to part 2 of our kinematics equations crash course, where we learn how to use these formulas with confidence and never get them wrong. Let's start with a quick reminder. The goal of kinematics is to describe motion. There are three main ways we describe motion mathematically, and the first is through average speed. Average speed is calculated by dividing the total distance traveled by the total time taken to travel that distance. We usually represent average speed using the symbol v, subscript average. D stands for distance and T for time. But this notation can be a bit bulky, so we often use a simpler format, a bar over the symbol for speed, like this, to show that it's an average. In this case, we usually drop the total labels, but keep in mind that both D and T still refer to the total distance and total time. Here's another key insight. Average speed doesn't always come from just one continuous trip. If you have several instantaneous speed measurements, you can calculate the average by taking the mean of those values. Now let's talk about acceleration. In physics, anything that causes a change in velocity is considered acceleration. But in this tutorial, we'll focus only on changes in magnitude, which means we're looking at changes in speed, not direction. You'll often see the Greek letter delta used to represent change, so when we write delta v, it means change in speed, or, technically, change in velocity. This description for acceleration then can be translated mathematically as acceleration is equal to delta v divided by delta t. This means acceleration is the change in speed divided by the change in time. We can be more specific about the change in speed by writing it as final speed v sub f minus initial speed v sub I. These three equations form the foundation for describing motion in physics. They focus on two key aspects of motion: speed and acceleration. But notice that within these equations, there are two essential reference quantities that anchor everything. Time, t, our absolute reference for when motion happens. It tells us when changes occur and over what duration. Distance or displacement, d, our spatial reference. It shows where the object is in space and how far it has moved from a starting point. Together, these references allow us to describe motion quantitatively and precisely, whether we're tracking a car speeding up, a ball in freefall, or any object in motion. With these tools in hand, we're now ready to solve real-world motion problems confidently and correctly. But not too fast. With the help of mathematics, we can simplify problem solving even further by deriving new equations, formulas that connect multiple kinematic quantities in a single expression. These derived formulas act like shortcuts, helping us solve problems more efficiently. And here's an important reminder. Using formulas is never a shortcut in understanding. It's only truly effective if you understand where the formula comes from and how to use it correctly. So instead of just memorizing, let's take the time to understand how these kinematics formulas are derived. Once you see the logic behind them, you'll gain both speed and accuracy in solving physics problems. Let's begin the derivation step by step. Typically, some textbooks only highlight 4 kinematics equations. But doing so creates an incomplete picture because it overlooks a very important starting point, a basic yet powerful idea: average speed. This equation right here is often ignored, but it plays a crucial role in understanding motion at a fundamental level. So in this course, we're giving it the respect it deserves. We're not brushing it aside. Instead, we're letting it stand proudly alongside the more famous 4 kinematics equations. After all, a strong foundation begins with the basics, and this one is as basic and as essential as it gets. Now, with that in place, let's proceed to derive the next equation using what we've already learned. Let's begin with a formula that we can use when average speed and time are not known at all. We can combine these two equations and rewrite the equivalence. By doing so, we removed the quantity for average speed. This simplifies to this equation. Next is time. We can derive an equation for time using the formula for acceleration. Once derived, we can replace the variable t in our solution. There, we've now derived a formula that connects just 4 quantities: acceleration, distance, final speed, and initial speed. This equation is especially convenient when solving for time seems difficult or even impossible. Since it eliminates time altogether, it allows us to work around situations where time isn't given or isn't easy to measure. It's one of the most useful tools in our kinematics toolbox, especially for problems involving sudden stops, launches, or any motion where distance and speed are the focus. Now let's proceed in deriving an equation that does not need final speed. The preliminary steps, as the previous one, are identical. However, this time, we will keep the variable t and remove the variable v sub f, or final speed. Again, we can do this by deriving an equation for versus sub f using the formula for acceleration. Once done, we can substitute it in our solution. This leads us to a formula that involves just distance, initial speed, time, and acceleration. This equation is particularly useful in situations where the final speed isn't given, and there's no easy way to calculate it. It allows us to solve motion problems confidently, even with limited information, as long as we know how far something travels, how fast it started, how long it moved, and how it accelerated. And with that, we've completed the full set of kinematics equations. The next time you see this symbol, it means average speed. This is different from instantaneous speed. The symbol A is always acceleration, while D is distance, and T is time. This set of formulas is the backbone of everything we'll do moving forward, from solving problems involving horizontal and vertical motion to analyzing freefall and projectile motion. Thanks for watching this episode of the Physics Chalkboard. If you found this lesson helpful, don't forget to like, share, and subscribe for more clear and engaging explanations in physics. Got questions? Drop them in the comments. I'd be happy to help you out. And if you're ready, join me in the next video, where we'll start applying these kinematics equations to real-world problem solving, step by step. Remember, understand first, memorize later. That's how you master physics. See you in the next one.